Hello everyone, in this we are going to see about 01 knapsack problem. So knapsack problem is general deals with number of items and the weight associated to it. Here 01 means 0 excluded and 1 included. So the problem is a classic optimization issue in computer science and mathematics. It involves selecting a subset of items, each with a specific weight and value, to maximize total value without exceeding a given weight limit. So we are gonna see in detail this problem. So the 01 knapsack problem, each item can either be included or excluded from the knapsack. The challenge lies in determining the best combination of items to achieve the highest value while adhering to the weight constraint. Because there are n number of items and each item has a weight associated to it. So if we have given a total weight, then we have to make combinations of items in such a way that it lies within or equal to the assigned weight. We cannot add items greater than the assigned weight. So we have to find the item combination in such a way that it always stays within the weight constraint. This binary decision making forms the crux of the problem. The mathematical formulation is that W will be the maximum weight of the capacity and N will be the number of items. Then Wi and Vi be the weight and value of item I. Like individual item will considered as I and each of it is associated with this particular weight and particular value. So the goal is to maximize the total value while ensuring the total weight does not exceed W. The zero-one knapsack problem is solved using the dynamic programming approach. Here, 01 basically means 0 is excluded, 1 is included, and so on. So, the popular method to solve the zero-one knapsack problem is using dynamic programming. This technique breaks the problem into sub-elements. Each a bigger problem will be solved in a simpler sub-problems, storing the results of these sub-problems to avoid redundant calculations. It provides an efficient way to find optimal solution. Greedy algorithm can also be used. While the greedy algorithm is often used for optimization problem, it does not yield optimal solution for zero and knapsack problem. Greedy method may lead to suboptimal solution as they may local choices without considering the global context of all the items. The zero knapsack problem has numerous real-world applications, including resource allocation, budget management, and cargo loading. Industries such as logistics and financial utilize its maximum principle for operations and efficiency in decision making. The zero-one knapsack problem is classified as a NP-complete problem, meaning it is computationally challenging to solve as the number of items increases. Understanding the complexity helps in developing better algorithms and approximations for practical use in large databases. So, in conclusion of the explanation, the zero and knapsack problem is fundamentally concept and optimization. The study not only enhances our understanding of algorithm design, but also paves the way for future research in approximation algorithm and heuristics to tackle larger, more complex instances effectively. So let's consider an example program. Given n items where each item has some weight and profit associated with it with a capacity of W. The task is to put the items into the bag such that the sum of the profits associated with them is the maximum possible. So let's consider an example. N equal to 3, weight is 4, profit is 123 and weight is 451. Here the output is 3. Let's understand why it is 3. So here the overall weight is 4 and the weights in the array of 451. In that case the possible combinations would be 4 and 1 because it is less than or equal to the weight allowed. So there are two items which have weight less than or equal to 4. If we select the item with weight 4, the possible profit is 1. So like if we select weight 4, then which it is equal to the allowed weight 4. So only 1 is the profit. But if we consider 1, we can take 1, 1, 1 3 times, still it will have a weight less than the overall weight. So the maximum possible profit is 3. Now that we cannot put both 4 and 1 because the total weight will be more than the weight allowed. So the second example is n equal to 3, w equal to 3 and profit is 1, 2 and 3, weight is 4, 5, 6. Here the overall weight is 3 but the weight in the array of 4, 5, 6, none of them can be considered because it is all greater than the weight allowed of 3, so the output is 0. Let's understand this with an example. Here there are items A, B, C, each has a profit and weight associated with it, with the maximum capacity of 5 is allowed. So here 3 items are there. First we will be considering one of the item and skipping one of the items. Similarly we will do it recursively. So first we are selecting an A and we are skipping A. If we are skipping B then A, then we will directly go to the B. We will be selecting B, we will be skipping B. If we select B, then we will be having a profit of 2, weight 7, profit of 7 and weight of 2. And if we select C on top of it, with B and C, we will have a profit of 18 and weight of 5. If we skip C, we will just have the profit of B, which is 7 and 2. And if we overall skip the B and go to C directly, we will be having a profit of 11 and weight of 3. If we skip C as well, then A, B, C, all 3 are skipped, so the profit and weight will be 0. From this section, the optimal solution is profit of 18, weight of B, where B and C is considered as it is within the capacity 5, within or equal to the capacity 5. And if we move on to selecting A, then the profit and weight is 1, 1. When then we select B, then the profit and weight is 8 and 3. If we skip B, then the profit and weight is 1, 1. With B, if we select C as well, then the profit and weight for A, B, C becomes profit 19, weight 6, which is greater than the allowed capacity. So this cannot be considered, this combination. We skip C, the profit is 8 and weight is 3 for AB. And if we skip B altogether and go on to the C, with A and C, the profit is 12, the weight is 4. And then if we skip C as well, only with the A, then the profit is 1 and the weight is 1. With this overall scenario, we can see ourselves the optimal solution is selecting B and C, which provides a profit of 18 and the weight of 5. So, the 0 and knapsack problem on a whole, the 0 and knapsack problem on a whole uh, uses this combination techniques and finds out which is an optimal solution for the particular items to be combined within the weight limit. The dynamic programming approach is followed in such a way that the subset of the items is created and an optimal solution is reached from it. Here we have another example of 1, 3, 4, 5 and with the value of 1, 4, 5, 7 considered. So in dynamic programming approach, we will be creating a dynamic programming table where the dynamic programming ij, jj represent the maximum value as achievable with the first 3 items and the weight limit is jjj. So the table has dimensions n plus 1, weight plus 1, n plus 1 by times, n plus 1, n plus 1, weight plus 1 initialized with 0. So the here the best possibilities is we are going to consider like a 0j equal to 0, 0i equal to 0 and all items have all have 0 items and 0 weight capacity. So the step-by-step solution is that if the row 1 can fit any capacity greater than 1, the maximum value is 1. For row 2, the capacity is less than 3, can't fit any of it, so carry over from the previous row. For capacities greater than 3, we will be comparing the items before it and the like the said item and this item before it. So the same approach will be followed to include or exclude based on whether adding the item improves the value. The process, the table will be completed by recursively comparing the items and adding one together, and the optimum solution will be reached in this situation for DP47 where the value has an item of 9. The items included are tracked back to find the subset that achieves the value. So the items 2 and 3 provides an optimum weight of 9. The first rows are considered 0, the first column is considered 0. So for the first item, if we just consider 1, then 1, 1, 1, 1, 1 will be there. If we consider to the next item, like for row 1 and column 1, or both will be 1, 1, 1, 1. Similarly, we will be considering for each row and each column and how the values are weight can be divided and used in such a way that the table is completed and the optimal solution is found at the DP table of 4, 7, which is 9. This is a general explanation of a knapsack problem. Thank you for listening.